Hi, thank you. I'm Iflai, and today I'm going to talk about a paper we recently worked on with my supervisor, Stephen Galbraith. And what's the content of this slide is that, so we talk about what's key exchange, and then we talk about SIDH Key Exchange, which is an isogeny-based key exchange, which is now currently still in the alternative option in the third round of this competition. And then there's a well-known adaptive attack against the SIDH key exchange, which is called GPST attack. And so that we cannot have a static to static key exchange from isogenies because of this adaptive attack. And there's one countermeasure proposed in Asiacrypt last year to construct a variant of SIDH scheme to prevent, and they claim this can prevent any adaptive attack from their skin. And finally, we show how to break it again to present a new variant of this GPST adaptive attack. So we start from the introduction. What's key exchange? Just Alice and Bob, they interactively or non-interactively exchange their public keys and obtain a shared secret. So this is the SIDH key exchange, and I will explain how it actually works later. But this SIDH key exchange is interactive. Alice needs to use Bob's public key to construct the shared secret. And unfortunately, this one is not adaptively secure. We will explain what's SIDH key exchange and why it is not adaptively secure later. So this is a brief intro, or say the setting of SIDH. And this prime of the following form. P is a prime number, 2 to the A and 3 to the B minus 1, which is a prime, and 2A is very close 3 to the B to prevent some torsion point attack. And we consider the elliptic curves as this following form, which is the Montgomery form, x3 plus x squared plus x equal y squared. And when we take 0 here, there's a special curve that is super singular, and the group order is 2 to the A and 3 to the B. And an isogeny from between these two curves is a morphism and also a group homomorphism between these two elliptic curves. And there's a proposition that if two curves are isogenous, defined over fp squared, then the group order are the same. And a codomain and an isogeny are uniquely determined by the kernel up to isomorphism. And here's an also special property of the torsion subgroup, which means that let's say there's an integer, positive integer n is not divisible by p, and En is when you multiply n time of this point P and you go to infinity, and this torsion subgroup will be isomorphic to Zn squared. Of course, Zn here means Zn quotient Mz. And so this is SIDH key exchange. The settings here is like this. E0, as we mentioned before, the torsion subgroup is isomorphic to these two-dimensional stuff. And we say it has basis, P2 and Q2. And the 3B torsion subgroup is also isomorphic to this stuff, and with basis, P3 and Q3. And Alice's secret key is a number between 0 and 2 to the A minus 1. Bob's secret key is between 0 and 3 to the B minus 1. So the kernel, or say the Alice secret key, is also secret isogeny phi A with kernel P is the subgroup generated by P2 plus SKAQ2, and Bob's kernel is P3 plus SKBQ3. And so this is Alice's secret key is the kernel, or say you say this secret integer. So everything in red, that means secret, and everything in blue, in blue, which means public key. So Alice's public key is EA, and her secret isogeny evaluation on P3 and Q3. So Alice's public key is a curve and 2 points. And Bob's public key is also a curve, EB, with 2 torsion points, the evaluation on P2 and Q2. So how do they do a key exchange? They compute, like for example, Alice take Bob's public key, and she computes phi A prime to obtain the curve that is called EBA. And the kernel of phi A prime is P2, is P prime plus SKA Q prime, where P prime and Q prime is the torsion point obtained from part of Bob's public key. So because, as we mentioned before, the codomain is uniquely defined by the kernel of the subgroup. So because if they perform honestly, then Alice and Bob will obtain the same curve. Partly they have different representation, but the J invariant will be the same because they are isomorphic. So what Bob can do here is that we're going to show GPST attack. So what Bob can do is that he manipulate his public key here and to see whether the shared secret is the same or not. And this can help him to determine the secret bit or the binary information of escape each time. So what will we actually do? We say Alice is the victim of this adaptive attack. We say Alice is entering into an oracle on input, EB, P prime, Q prime. These three, EB, P prime, and Q prime, correspond to Bob's public key here. And then EAB is the curve given by Bob. So Alice, or say the oracle, will return 1 if and only if the curve here, EAB and EBA should compute. They have the same J invariant, or say these two curves are isomorphic. If so, she return 1. If not, she just return 0. And also, to use this attack, we need a simple assumption. That means if G1 and G2, these two subgroups, if the order is quite small compared to P, then we can assume that EB quotient G1 isomorphic to EB quotient G2, which is if and only if G1 equal to G2. This fact is generally not true, but if the order of G1 and G2 is small, then this holds with quite overwhelming probability. So Bob computes EB and honest. So what Bob can do now, he wants to extract Alice's secret key. So Bob firstly honestly compute EB and phi B P2 and phi B Q2 honestly, and then he replaces the P as the same as P prime, and Q prime as is Q, and additionally add Q to the A minus 1 P. And we are going to show that Alice will return 1 if and only if the less significant bit of Alice's secret is 0. So we are going to show this. Alice return 1 if and only if her secret key is the least significant bit of her secret key is 0. Oh, sorry. So we are going to show this SK, Alice secret key, is even if and only if these two subgroup are the same, which means P prime plus SKQ prime equal P plus SKQ. So we expand this. This is the P prime and Q prime are the points manipulated by Bob, and we expand this as P, and we expand Q prime as Q plus a to the a minus 1P. And then we use this probably distributive law, and you got this P plus SKQ, which is the same as before, but this one additional term that is SK to the a minus 1P here. So this term will go to 0 if and only if SK is even. So that's why Alice will return 1. And if and only if her secret key is even. And so by using, and also this attack allow Bob to extract even more bits by using this method recursively and extract Alice's whole secret key. So like Alice's secret key is a number between 0 and 2 to the a minus 1. And by using this oracle 8 times, then Bob can extract 4 secret key of Alice. So a countermeasure proposed by in Asiacrypt 2021 by Boris and Christoph is they use the commutativity of the diagram of two parties if both parties are using the value formula. We know these two diagrams will lead to the same the isomorphic curve, but moreover in this paper they show that the curves are identical, and also the evaluation is commutative, which means that if you compute phi b prime and phi a, which the result will the same as phi a prime compose phi b. So this is the idea they use, because you can observe that if Bob in this attack, Bob want to extract Alice's secret key, he has to manipulate this point here, and because he manipulates this point here, these authors probably expect that this will make this commutative law not hold. So this is the mechanism they construct. The left-hand side part is quite similar to the SIDH Key Exchange, and they construct a mechanism they call key validation mechanism, and this is just used to check the commutativity we just mentioned. And we will explain a bit their scheme later. So with this key validation mechanism, they also provide with a proof of this mechanism, and this proof, the theorem is very strong, which means that only correctly formed public key can pass the mechanism. So which means that if Bob manipulates the point, then Bob will always get rejection from Alice. So this means that the information leakage of the mechanism is negligible against any adaptive attack, because this mechanism will only return 1 if your input is the correct public key. And this also means that we can have a static key exchange, or PKE, from SIDH against any adaptive attack. So it seems very good so far, because the theorem is very good. But the problem is that the theorem and also the proof is incorrect. And we will, even based on this fact, we present a variant of GPST attack against their mechanism and extract the secret key of Alice, and the number of oracle query is the same as GPST attack. So this is the key they call HealS SIDH, which means that they make them immune to any adaptive attack, so they call HealS SIDH. And together with the key validation mechanism, they've made a few changes to SIDH here. Like we have the torsion subgroup is 2 to the A before, and now the torsion subgroup is E 2 to the 2A. And the basis for bar is 2 to the 2B here now. But Alice's secret key is still between 0 to 2 to the A minus 1. And so it's the same for Bob. And the kernel now has the spatial form 2 to the A P2 plus SKA 2 to the A Q2. So the left-hand side part is quite similar to SIDH, and they have something special in this diagram here for Alice. This information will be used to check the commutativity to see whether the commutativity will hold for this part. So this is the key validation mechanism they construct. But of course, we don't want to go into these things too detail. So I will just explain how we have another adaptive attack based on the key validation mechanism. So again, we say Alice is the victim of our adaptive attack again, and say Alice is an oracle taking on input EB, RA, SA, RAB, and SAB. We have more points here because Alice needs more information to do the commutativity check. So Alice is an oracle on input. Then on this input, she returns 1 if only 3 following equations hold. And the first one is just a simple pairing check we also have in SIDH before. And the second one is the check for the commutativity we just mentioned. And where phi A is from EB to EBA, and with the kernel, and the kernel is also the information is given by Bob. So intuitively, I guess the authors may think if you want to manipulate the point here, this will make the first equation and the second equation will make them difficult or impossible to hold. So they expect this can prevent the adaptive attack. So what we do here, we have a lot of input here we can do, but we still manipulate 2 points, RA and SA here, and we will manipulate RA and SA to extract the secret information of Alice's secret key. So of course, this attack involves a lot of complex calculation, but we don't want to go into these details in these slides. So I will just explain the high-level idea of our attack and how it works. And firstly, we have some few facts or say lemma. If 5B is an 3B isogeny, and the evaluation of the two torsion bases will still be a 2 to the A torsion basis on the new curve, because it will not kill any 2 torsion subgroup to the point at infinity. And recall that this is the relation from the second and from the first and the second equation, And this coefficient here is part of the secret information from Alice. And we notice that this ABCD coefficient has this this relation with Alice's secret key. So which means that A plus SKC equal B plus SKD equals 0 modulo 2A. But remember that the coefficient of ABCD is 2 to the 2A, and SK only is between 0 to 2A. So we can say that the lower bits information of A and B are related to SK, are related to Alice's secret key. So firstly, we extract the first secret B of Alice. So we can rewrite these two equations as this following form. So as the following form, we write phi A prime RSA with the coefficient here in the matrix form. And our goal here, the way we extract the first bit, is that we find two spatial matrices, P1 and P2, such that P1 acts on this matrix. This equal the matrix P2 is conditioned on the parity of ABCD. And also we require the determinant of P1 is 1. We made this for the pairing equation. If we find this kind of matrix conditioned on the parity of ABCD, then we can apply RA prime SA prime as P1 RASA, and RAB and SAB prime to be P2 RAB SAB. So this can give us information. Yes, this can give us information of Alice's secret key, because if the commutativity hold, which means that means Alice will return 1, so which means that we can know the information of ABCD. So actually, the matrix we find is as the following form: 1, 0, 2 to the A minus 1, 1, and P2 is the identity matrix. And this commutativity will hold if and only if AB equals 0 modulo 2. And recall that we have these equations. And also we prove that both C and D cannot be both even. So which means that SK is even in this case. So which means that if we apply this matrix, we give this input to Alice. If Alice return 1, which means the secret key is 0. If Alice return 0, then which means that the least significant bit of her secret key is 1. So currently it goes very well. We extract the first secret key. So the next goal is to extract the second bit of Alice's secret key. So because we have this following theorem, so we can rewrite AB in terms of SKA-C and SKA-D. So we write as this form. And the next step here is that we use the homomorphic proposition of the isogeny, because isogeny is homomorphic, right? And to launch GPST attack again. So concretely, if we let RA prime as this form, and where SK0 is SK, we just extract. And the first equation will hold by some calculation. The first equation will hold if and only if the secret key is 0. And also we need to check the kernel, because we need the kernel used by Alice is the same. If Alice produce a different kernel, then of course we don't have this homomorphic proposition. So we also find that the kernel are the same as before. But unfortunately, the pairing equation will not hold, because you can see that the You can see from this equation, you calculate the determinant of the matrix, you will find the determinant is the original one to the 2 to the 2a minus 2. So the pairing equation will not hold. So we need to so at the current stage, we only manipulate RA prime for this case. So to solve this problem, we also change SA prime to make the pairing equation hold. So what we do here is that firstly, we assume SK is invertible, which means that the parity of the SKA is 1. So we let SA prime as this following form. And of course, we already know that this RA prime will hold if and only if SK1 is 0. And then by assigning this special SA prime, the second equation will hold if and only if SK infers the first bit, the second bit of the SK infers is 0, which means that the second bit of SK is 0. And we check the pairing. So now the pairing holds because you can see the determinant, which is equal to 1 modulo 2 to the 2a. So that's why the pairing equation will hold in this case. And also the other one is the kernel, and luckily the kernel is the same. So now we extract the second bit, and you can use the similar technique if the SK is invertible in this case. So what's the problem? So how to solve the problem if SK is not invertible? So we give some fast review about what we have done. Firstly, we want to make sure the pairing always hold and the kernel always the same. And we manipulate to see whether these two equations will hold depending on the secret key of Alice, the secret bit information of Alice secret key. So if SK is even, then what we do here is that we find the spatial RA prime and SA prime as the following form. I wrote something in yellow, means that I will explain a bit later. And then we check the first equation, and the first equation in this case will always hold. And then the second equation will hold if and only if the second bit SK1 is 1. And also we also check the pairing equation. You can see you calculate the determinant of this matrix, and you will find the determinant is 1 modulo 2 to the 2a. And also the kernel is surprisingly the same as before. So this is so if the first bit of SK is 0, then we can use this method to extract the second bit of the SKA. And yes, and how about if it is the second bit is also 0? We can adjust this one. So to extract the third bit, we change this 2 to this 3, and this SK1. Then the next bit will still be even. Will be 1 if and only if this equation holds. So by adjusting this part, we can extract the secret bit information if you always extract 0. So until we extract 1, what we do here, we manipulate RA prime as before, and we manipulate SA prime with respect to the quasi-inverse of SK modulo 2i. this is the term we invent by ourselves, so it is not a formal mathematical term. So a quasi-inverse means that it like 24 is a multiplied by 3 modulo 32. And so the quasi-inverse is we just focus on the non-power of 2 parts, the inverse of 3 inverse. So we do the same as before, and we calculate, expect the quasi-inverse of the next bit we want to extract, and use the similar technique as before. And we can extract the whole secret key of Alice's secret key information, and the efficiency is the same as the original GPST attack. So the mechanism not only slow down the SIDH protocol, but also give no advantage to prevent adaptive attacks. So here we give a brief summary. In Asiacrypt last year, some people present a new variant of SIDH with key validation mechanism. And the client schemes are immune to any adaptive attacks and give the first efficient static-to-static key exchange, or say public key info encryption from SIDH. And we present a new adaptive attack, which can be viewed as a variant of the original GPST attack to break the crypto system. And we also provide some generalization for our results, like not just attack Alice, and also attack Bob, and also the more general form of Alice's secret key. So now the problem is still open now again, whether we can have an efficient static-to-static encryption or public key encryption from SIDH. This is still an open problem. And that's all. Thank you for listening.